We'll start today's session. Okay, last class we discussed about different service mechanisms and services, right? And today we move on to some of the classical encryption techniques, some breakthrough techniques which have been found in the history of cryptography. Okay, we'll be discussing now. So we'll be starting with the discussion on substitution techniques. Then we move on to transposition techniques, then rotor machine and steganography. So as a name denotes, in substitution techniques, the characters in the plain text, okay, characters present in the plain text are going to be simply substitute or replaced, okay, replaced with some other new character or new alphabet kind of things. Whereas if you go with the transposition technique, okay, the characters in the plain text, their positions, okay, that is the position in the entire message is allowed to be changed. Only positions are changed here. That's a name called transposition techniques. And here the entire character is going to be substituted or replaced with a new character. So in this comes the substitution techniques. So under the substitution techniques, we'll be going through Caesar cipher again. Then how the Caesar cipher have been evolved towards monoalphabetic cipher, then polyalphabetic, and Playfair and Hill ciphers, some of the key breakthrough techniques which have been found in the history of cryptography. Like, to start off with, we already had a Caesar cipher's brief introduction. So Caesar cipher is also called a shift cipher or Caesar's code or Caesar shift. Okay. So in this, you can able to see that each and every character or letter in the plain text is going to be replaced by some other alphabets, which is a fixed number of questions from the original plain text. Right. So as we already saw, Caesar cipher, he will be choosing number 3 as a key, so that he's going to change or he's going to replace the alphabet, which is 3 positions towards the right hand side of the original plain text value. Right. So here you can able to see there is a plain text here, which means meet me after the toga party. So generally we'll use small letters for representing a plain text and capital letters for ciphertext. Okay, so Caesar cipher will go with the key as 3. So you can able to see we have a alphabet like meat. This is the first word. So if you take letter M and if I replace it with the 3 portions, 1, 2, 3. Right. So M will be replaced with the P here. That's why you can able to see. And these are the ciphers for respective plain text in the English alphabet. So E, you can see E is present here, 1, 2, and 3. So E is replaced with H here. Right. Like this, they will be substituting each and every characters with the ciphertext here. And in the reverse manner, that is in the decryption part, they'll be shifting back for the 3 positions here. Right. So generally, if you want to represent a Caesar cipher mathematically, they will go with just simply will number the positions of each and every alphabet starting from 0 to 25, so that you can able to write the ciphertext as a encrypted version of the key here used as 3 and the plain text values positioned here. So mathematically it is written as P plus 3 modulo 26. Okay. Why we are choosing this 26 in the sense, since you are using English as a language, totally we have 26 alphabets. So we go with this modulo 26. So how many of you are, have a knowledge about modulars or modular operations? Can you raise a hand? We'll be having a detailed discussion on modular operations in module 2, but Caesar cipher, we should know what is at least the basics of modular operation. How many of you know? Can you raise your hand? Okay, how many of you don't know or having only some partial knowledge or bits and pieces of modular operation? Can you raise your hand? Right. If you see a simple modular operations, for example, if I say 5 divided by 3, what I will do in the sense, okay, I will take 3. Sorry. So I will take 5 and divide by 3 to go 1 times, and I'll be getting the quotient as 1 and the remainder as 2. Same operation will be done if I write 5 modulo 3, the answer will be taken only the remainder value. So answer will be 2 alone is the answer. So why we are going for this kind of thing in the sense, for example, why we are going for this modulo operation? Assume we take any, okay, we will take the word THE here. Okay. So the word is T, H and E. So T, the original position of T is 19, right? So yeah. So here we are going with the device. Okay. Generally, first I will go with the word THE. So T, the position is 19. So what I will do since 19 plus 3 is the key value, and I go with modulo 26. So 19 plus 3, the answer comes for 22. Right. 22 mod 26. 22, we can't able to divide 22 with 26, or simply what I'll do is I'll go 0 times. So answer will be again 22, the remainder. So 22 is here W, right? So the T will be replaced with capital W, and H is 7. So I'll be going with 7 plus 3 mod 26. I'll be again ending up with 10 as answer. So for 10, I got K as a value. So H will be replaced with K and goes on. For example, here you have anything like, assume that we are going with Y. Okay. The position is 24. Yeah. So Y's position is 24 here. Right. So if I go with here 24 plus 3 mod 26. Why we are performing this modulo here? For 24 plus 3, I'll be getting 27. Right. I don't have any alphabet beyond this 25. So 27 mod 26. If I take, what will be the answer? Can anyone tell?
1.
1. Yeah. So 1 I'll search. 1 goes to B. So I'll replace the small letter Y with B here. And we'll see small letter Y is replaced with B. And this is how a Caesar cipher works on. Right. So now people started to make this Caesar cipher as a general or generic expression. That is, instead of fixing the value of key K has to be 3, they want to generalize the expression like this. Let's K comma P, where K will be the number of positions you're going to shift. So P plus K modulo 26 will be the general expression for Caesar cipher for encryption. And for decryption, okay, we will be using a decryption algorithm D. Again, the same key is used. And here I'm going to subtract the key called K. Since I have performed this addition here, we will go with subtraction here. But in cryptographic point of view, we don't call this as a subtraction. The voice is breaking up. Is it clear now? Am I clear now?
Yes, sir.
So generally for decryption, you will go with the subtraction of the key value. But in from cryptographic point of view, we won't call this as minus K as like minus of the key value. We'll call this term as an additive inverse. Okay. So whenever you are going to perform any addition in the encryption, you will be performing a subtraction operation. But I used to call this entire term along with this negative sign as an additive inverse of the key K. So if you move the Caesar cipher to be a generalized cipher, assume that now you're going with a key called 15, and I want to encrypt a message hello. Okay, you can able to see here the positions of H, E, L, L, and O. You can able to see from here. H takes a value of 7, E takes a value of 4, L takes a value of 11, and O takes a value of 14. Right. So they went with this 7, 4, 11, 11, and 14, and I'm going to perform the encryption here. Simply the key is here, it is 15, and you have to substitute the values of your plain text values then and there. So you can able to see here is 7 plus 15, So 7 plus 15, what will be the answer? 22, right? So 22 mod 26, I'll be getting again 22, so W. Here 4 plus 15, I'll be getting 19, so here no issues. In this case, 11 plus 15, I'll be ending up with 26. 26 mod 26 is 0, so I'll be writing it A because A, I hope everyone know, 0 is the question of A. Similarly, now at last we are having 14 plus 15, which gives me 29, right? So 29 modulo 26, I'll be ending up with 3. So 3 is this one. If you go with the decryption process, so here we got the encryptions and the ciphertext to be WTAAD, right? And for decryption, simply I'm going to perform a addition of additive inverse. I used to call addition of additive inverse. Right. So if I have 22, the 22 minus 15, I'll be getting 7. So generally I took the 7 value here and I got the plain text back as hello. Assume this condition 0 minus 15 mod 26. So simply it is minus 15 mod 26. Generally this mod operation, when it is used in cryptography, we can't able to deal with negative values because we don't have any negative positions here. So I have to convert this negative value into a positive value. We'll be discussing this in module 2, but now itself I'll just give a glimpse of this. Right. So to convert this minus 15 into a positive value, what we have to do in the sense, you take the negative value which you find and add the modeling. That is modeling something but this value 26. So minus 15 plus 26 will give me 11. Then you go for modulo of 26. So 11 mod 26, I'll be ending up with 11. Right. Then 3 minus 15, you'll be getting a value as minus 12. Okay, mod 26. Again, if you want to convert them into a positive value, minus 12 plus 26, fourth thing, mod 26, will be ending up with plus 14 mod 26. So 14 will be getting the value of 0. Sorry, oh. Right. So this is how a generalized Caesar cipher works on. Okay, and we used to call this generalized Caesar cipher, which is using this addition and subtraction as additive cipher. This is the improved version of a Caesar cipher called additive cipher, where we are using this is your encryption algorithm. So here we are using your simple math of addition and the modulo operation inside this using the key called K and input of plain text to get the ciphertext. And here we are using the same key for decryption, but only a small variation in the mathematical part. Here we are adding with the additive inverse, right? So I'm having an additive inverse, then followed with the modulo operation of 26 to get the plain text back. Hope you people are clear with this one. If anyone have any doubts, you can ask me. If it is clear, kindly raise your hands regarding this additive cipher and Caesar cipher. Thank you, Raghvendra. Thank you. Now we move to the cryptanalysis of this Caesar cipher. So what are the drawbacks they have found in Caesar cipher? If suppose encryption and decryption algorithm is known, okay, that is the attacker knows that you are using Caesar cipher, even if he doesn't have a knowledge about the key, he can able to find or crack your ciphertext easily, because if you are using English as a language, you'll be having only 25 keys. Simply speaking, only 25 keys will be present here. Okay, because I mean, I think, yeah, here the K value will take only from 1 to 25. It won't take 0 or 26. Can anyone tell why we can't take 0 or 26 as a key value? Any idea? Why
So the
can't?
plain text will remain same.
Yes, then there is no use of encryption itself if you use 0 or 26 as a key. Right.
Yes.
Even if you go with 27, 28, also there is no use, because if you go with 27, 27 mod 26 will be getting the key value as 1. 28,
Yes, sir.
28 mod 26, again the key value will be 2. That's why they are sticking with 1 to 25 here. Right. So this is a drawback, that is we can have only 25 keys. So he can simply perform a brute force attack. Brute force attack is like a trial and error method. Assume that this is the ciphertext which has been intercepted. What he is doing then is simply using his calculators or using his system. He is substituting each keys from one and goes on. And when he reaches k value to be 7, he got some meaningful message here. It is not very secure. So he just broke the Caesar cipher. This is one of the major drawback in Caesar cipher. There are also other attack which can also be performed on Caesar cipher, right? Which is using this chart. This chart is a generalized chart provided by Oxford University people, which is denotes the frequency of characters in any English letter or any English sentence. If you take, sorry, any English word or any English sentence, it shows how much frequent a letter is going to be repeated. Among this, E is the most repeated letter with a 12.7 times of repeatancy. Then T, A, O, I, N, S, and goes on. So generally we used to number them as 0, 1, 2, 3, 4, and goes on up to 25. 25 is for Z. Right. Using if a person has this chart with him also, he can able to perform an easy attack. Okay. That attack is called a statistical attack. So if he has this frequency of repetition chart with him, he can perform a attack called statistical attack on Caesar cipher. Assume that this is the biggest some cipher test which the attacker has come across. So what he will do in sense, he will take the cipher text and he will count the repetition of every letters present in there, and he will find which is the most repeated or most common character in the entire cipher text. So in this example, he found I to be repeated 14 times. Okay, so he found I to be repeated 14 times. Okay, and V is repeated 13 times and 12 times and so on. So his concern is only is I. Okay, so he found this I, which is the most repeated character. Now he looking his table here, and he is finding I is present in the 4th position. That is from 0, not from 1, 2, 3. From 0, 1, 2, 3, 4. He finds I to be present in the 4th position here. So what he did in sense here, he simply substitute the value of k to be 4, and he can able to directly decrypt the message. The house is now for a sale for $4 million. It is worth more hurry. It is worth, more hurry before the seller receives more offers kind of thing. So this is a plain test he just decrypted. Okay. So this is the attack called statistical attack, which also reveals the weakness of the Caesar cipher. Right. So anyone have any doubt in this cryptanalysis of Caesar cipher? You can ask me. If it is clear, raise your hand so that I will move on to the next one. Okay. Right. Now we move on to our next improved version called multiplicative cipher. So here they're going to perform, instead of addition, they just replace with the multiplication here. Yeah. And able to see there's only a small variation compared to a multiplicative cipher called with the multiplication they are doing here. But here they don't go for any division here. Instead, they multiply with k inverse. Okay. This k inverse is called as multiplicative inverse. Multiplicative inverse of the key k. It's not a division here. So why can't you go with p by k? Because if you go with the division, you'll be ending up with the decimal values. And in cryptography, we are not going to use any decimal here. We'll be having detailed discussion of how the multiplicative inverse computation can be done in module 2. But here, not to understand multiplicative cipher, just have the knowledge of this is a multiplicative inverse, not a division. That's all. Right. Let's see an example here. Okay. That's why I just removed the decryptive part here. The decryptive part we can learn in the second module. So generally, if for example, here we have the message called hello, as a plain text, and the key has 7. Yeah. So here we'll be getting 7 into 7. So we'll be getting 49 mod 26. So 49 mod 26, what will be the answer? 49 mod 26. Answer? You can use chat
30.
box. 13. No, can you be more specific? It's not 13 actually. You have the answer in the slide itself. Simple guys. 49 mod 26. You go only one time. Right. The answer is 23. So 23 mod 26 again 23. We'll be getting the ciphertext as 6. Right. 4 into 7 will be going with 28 mod 26. So I'll be getting 2 and goes on. Yeah. So this is how multiplicative cipher works on. Now they improved this one with adding the two operations of addition as well as the multiplication. This cipher is called Affine Cycle. Okay. You'll be getting more numericals from this Affine Cycle during examinations. Right. So here you can able to see how the process works on. Initially the plain text is given as input. First I am performing a multiplicative cipher. The K1 is a key used for multiplication and K2 is a key here used for addition. Right. So here I am creating a temporary text T using the plain text value P, K1. The entire thing is undergoes a modulo operation of 26. Next I am taking this T and I am performing an additive cycle. Simply I am adding the key K2. Then I am performing modulo 26. Then the output is taken as a ciphertext. So this is a double encryption you can able to say, or double mathematical process altogether act as an encryption algorithm here. And in the decryption part, here you people have to listen carefully. So this is going from bottom to top. So whatever the operation you are going to do at the end has to be done the inverse version of the decryption first. So here at last you perform this addition. So here I'll be performing it with the additive inverse. So here K2 will be used as a minus K2 is nothing but the additive inverse, and the output will be taken as a temporary output, and this will be taken here which will be multiplied with the K whole inverse, which is nothing but the multiplicative inverse. Then which will give me the plain text back. And here the K1 which is used for multiplication, the same K1's multiplicative inverse will be used in the decryption part. Okay, so if you want to write it mathematically, I'll be writing P times of K1 plus K2. The entire thing modulo 26 will give me the ciphertext, and C minus K2. Then I'll be multiplying with the multiplicative inverse of key K1. Okay, then I'll perform the modulo operation. So in this, as I said, K1 the whole inverse is a multiplicative inverse of K1, and minus K2 is additive inverse of K2. Right, this is a general structure of affine cycle. Yeah, someone have some doubts?
So the range of K1 and K2 are still again 1 to 25, right?
Yes, yes, yes.
So even now we can break with 625 trials, right?
Yes.
Earlier yeah.
The number of trials is increased. That's all. They don't climb. This is a best cipher technique. This is how cryptography has been evolved. We are just having a glimpse of this. Even if nowadays with the present day scenarios, this type of techniques are not at all used, because it's very simple with the present day coding techniques, and with technology they can easily crack anything if you have these things. This is for you understand. Yeah.
Okay.
So this is how your affine cipher will look like. That is, we'll be providing you with a plain text in examination, and we'll be giving you a key pair. So whenever a key pair is provided, the first one will be taken as K1, which will be used for multiplication, and second one is a K2, which will be used for addition. In examination, we won't say this is for multiplication, this is for addition. You people have to know it yourself, know by yourself. Okay. So here you can able to see you have the same hello encryption. They first perform the multiplication, then plus 2. So 49 plus 2 mod 26, which will give me 51 mod 26, which gives me the answer 25. In the decryption part, they again go for the subtraction, then they go for this multiplicative inverse. We will see this how the multiplicative inverse is computed in the next module. So after you know that, then you can able to easily solve this affine cipher. Okay. I mean, affine cipher's decryption part. So for 7, you'll be getting a different value. In this case, you'll be getting answer to be 15. So the multiplicative inverse of this one. So how come this 15 arrived in, we will see in the next one. Right. So I want everyone to be clear with the concept of this affine cycle. So you should know how to calculate this encryption part. Decryption part we can learn after your second module, especially this multiplicative inverse part. So apart from this, if everything is clear regarding affine cipher, you can raise your hand. If you have any doubts, you can ask me. Okay, I hope this is clear. Right. Now we move on to a next one called monoalphabetic cipher. So as I say, people started to find easy ways to crack this kind of Caesar-based ciphers where we have only 25 possible keys. Okay. They moved to a, encryption technique called monoalphabetic cipher. So here, instead of having only single keys, we have 26 alphabets in English, right? So how many ways I can able to shuffle this entire 26 alphabet? So if you see, I can able to shuffle them nearly 26 factorial times. Or simply I'll be getting 4 into 10 power 26 combinations I can able to get. So instead of having 25 possible keys, I can choose any one from this 4 into 10 power 26 combination. This is one of the combinations. This is one of the combinations. Right. So they'll be having this lookup table. Okay, this lookup table will be there with both transmitter as well as with the receiver. Oh, so transmitter will encrypt using this lookup table. Okay, for example, say this message is easy to encrypt but hard to find the key. This is a simple message here. For example, if you take the letter is I and S. So for I, I'll be representing with F. For S, I'll be representing with V. There's no stipulated rule that I means this is 3 questions here. S means this means 3 questions. It's totally a shuffled version. So this will be replaced with F and V. Right. So this here is replaced with F and V here. Right. So this is how a monoalphabetic ciphers work out. Then from monoalphabetic, we started to develop a next version called polyalphabetic cipher. This make the encryption algorithm look somewhat complex compared to your affine ciphers or multiplicative ciphers. So what is the major objective of this polyalphabetic cipher in sense? Generally, if you take a plain text, okay, from plain text, I'll be creating my ciphertext, right? Ciphertext. Generally, one character in plain text will be related to one character in ciphertext till now whatever we just saw. So they want to make this relation one to many, not to one to one. There's one character in ciphertext should have links for multiple characters in the plain text. 1 second, guys. 1 second. Sorry. Okay, they want to create one to many relationship. Okay. So for in this criteria, the first developed polyalphabetic cipher is called auto key cipher. So what they did in sense, they have a stream of plain text. For example, we just saw a message called hello, right? So in this H takes P1 value, V is P2, N is P3, then another N and O will be a P4 and your P5. And the respective ciphertext are C1, C2, C3. So to create this kind of variations in previous examples, we used only a single key called K, only single value. But here they wanted to create a stream of keys, and this key is generated with the help of plain text itself. So they have the initial value called K1, which will be used as a key. K1 will be used to convert the plain text P1 into C1. Okay. And the second key called K2 is nothing but P1 value itself. K2 will be used to convert this P2 into C2 and goes on. So if you want to write this encryption algorithm, here I have a suffix called CI PI and KI. So for each and every ciphertext, I'll be having a unique plain text which is encrypted using a unique key. Okay. But here to create this stream of keys, they are making use of the plain text itself. We'll see an example so that you'll get a clear picture. Assume that Alice and Bob are going to use auto key cipher to transmit and receive a message. And they have the initial key value K1 to be 12. Okay. Right. Now the messages attack is today. So what they did, in since they took the plain text, they wrote like this attack is today, and the respective positional values are 10 here. 0, 19, 19, 0, 0, 2, and goes up to 24. I mean, this is general alphabetic portions of from A to Z. Give you a number from 0 to 25. Now they're creating a key string. They have the initial key value K1 around 12. Okay. Now the K2 is nothing but the P1 value. Next, they pushed everything downwards. Yeah, like this, except the last one is this one. Once they got the key stream, now they're creating a ciphertext value. What they did, in sense, they performed addition of this positional value and the key string, and they took a modulo operation of 26. Okay, whatever they're going to perform, add here. So, for example, in this case, if you take this one T, so okay, here they're going to add is 19 plus 19, which will be I'll be getting as 38 mod 26, which will give me answer as 12. Okay, so 12, the value is M. And you can able to see the same M is produced in different way. Here it is 0 plus 12, which gave me 12, but here 19 plus 19 gives me 12. Right. And if you trace back the relationship between the plain text and this 12, you can able to see, if you trace back, otherwise we'll just take this yes. Okay. This yes, how it is traced back. So I got 18 as output. To get this 18 as output, I used a key called 10, and I used a value of I called 8. But this 10 is obtained from the other plain text tree. So you can able to see the two plain text are related to create this one ciphertext here. That's called one-to-many relationship. This is one of the examples. This is the first and foremost cipher in polyalphabetic cipher called auto key cipher. Anyone have any doubt in this one? If it is clear, raise your hands. Okay. It is fine. So these are the positional values as we just saw. Now move to a next one called Playfair Cipher, one of the breakthrough technique, okay, which is also coming under a polyalphabetic cipher. Okay, it has many names called Playfair Cipher, Play Square, or Wheatstone. Playfair Cipher. The person who founded this technique is called Charles Wheatstone, but it obtained the name Playfair because Lord Playfair is a person who was promoting this entire technique. This technique played a major role during the times of Second Boer War, World War I, and during World War II. What is the unique and specialty about this Playfair cipher instance? In this technique, if you want to encrypt the plain text, if you see the techniques which I have seen so far, we'll be taking one character from the plain text, right? Whereas here, I can able to take two characters at a time from the plain text, and I can able to encrypt for the ciphertext. That's why it's called, I can able to take bigrams or diagrams, okay, instead of single letters. So this Playfair cipher is harder when compared to the previous simple substitution technique. So you can able to see at the end of this Playfair cipher. Okay. First, before learning the encryption technique, first you should know how to create the keyword or key phrase. Okay. So what is this keyword or key phrase? In sense, in Playfair cipher, we'll be using a 5x5 table or like a bots or a matrix kind of thing. So 5x5 means there will be 25 entries in the keyword itself. 25 entries will be there. Okay. Then using this keyword, then and 4 simple rules are there to create the cipher text from the plain text. Okay. For today's class, we learn how to create this keyword itself alone. Next class, we move on to the creation of the encryption process. Okay, because now time won't permit. Yeah. So if we start with the keyword phrase, there are two ways we can able to create a keyword. There is keyword bots or key, this 5x5 thing. Okay. And that we can able to ask, say there are only 25 entries, but I want to accommodate all the 26 alphabets. All the 26 alphabets has to be placed inside this 25 boxes. How it can be done? So Playfair gave two options for the users. One is either you can omit the letter J or you can able to omit Q. This is one option. Other option, you have to put the letters I and J in the same place. Okay. As per our condition is concerned, that is generally used to solve in the examination point of view and course point of view, you'll be going with the second condition. Okay. Mostly we'll be using I and J in a single box itself. So whatever the rule you are going to follow, it should be intimated to the receiver also generally. Right. So this is one way of placing this 25 characters inside this 26. Sorry, 25. Sorry. 26 alphabets inside this 25 boxes. Now we'll see how these 25 boxes are going to be filled. Okay, generally, there is one way, that is they will be providing a keyword called any keyword will be provided to you. In this example, they provided you a keyword called monarchy. Okay, this is a keyword called monarchy. Using this monarchy, I have to create a 5x5 box. So first, I will start filling in the row wise, starting as M, O, N, A, R, C, H, and Y. Okay. Now I'll be starting filling my next empty boxes with the letters which are not present in the keyword. So A is there, so I won't start with A. B, C is present here. Next is D, E, F, G, H is already present, so I won't write. So in this case, I'm using the second condition, that is I'm going to place I and J in the same box. Okay. Then K, L, M is present here, N is here, O is here, then P, Q, R is here, S, T, U, V, W, X, Y is present here, and Z. Okay, this is how they will be filling the single boxes. And suppose, assume that you are having a keyword where there are repetitive letters in it itself. For example, assume that you are using a word called apple. So apple means I will be filling first. 1 second. Here I will be going with A, P. Again, I won't go with P because P is already repeated. So I will go with L and E. Okay, then I will be start filling in the other missing characters here. Okay. So this is how we will be filling this keyword phrase. So anyone have any doubt in this part? How to fill this keyword bots or 5+1 boxes? If you have any doubt, kindly ask, guys. Because without this step, we can't able to perform the encryption process. That's right. If it is clear, raise your hands. It's very simple. Yeah. Okay, this is one way you will be allowed to create this 5x5 bots. Other way, they won't provide you with any keyword or anything. Simply, they will provide you with the direct bots itself. That without any keyword, they will be provided with the 5x5 bots with you. So you can either use this kind of bots if they provide. Otherwise, if they provide with any keywords like this, then you have to create these bots on your own. Then you have to start the process of encryption then. Right. So with this, we'll wrap up today's session. In next class, we will discuss how we can able to perform encryption, that is Playfair encryption using this keyword. Right. There are only four simple rules we will discuss in the next class.